Let's talk about the similar triangles that are created when you draw an altitude inside of a right triangle. But first, let's review some basic triangle information and information about similarity. For example, could you figure out the measure of angle M and the measure of angle H in these two triangles? Well, yeah, we could use the corollary to the triangle sum theorem to say that since this is a right triangle, the two acute angles add up to 90 degrees. So the measure of angle M would have to be 37 degrees. And likewise, since this is a right triangle, I can add these two acute angles together and set it equal to 90 degrees as well. So I find out that they have the same angle measurements. They both have a 90-degree angle, they both have a 53-degree angle, and they both have a 37-degree angle. So that means that these two triangles are similar. So let's review how to write a similarity statement. To name a triangle, you write a triangle symbol, and then the three vertices of a triangle in any order that you want to. But since we're writing a similarity statement, the letters must be written in a corresponding order for both of the triangles' names. So for example, if I choose to call the first triangle, the green triangle, MRC, I have to call the other triangle QHB, because that goes in a corresponding order. If I call the first one MRC, that's the 37, the 53, and then the 90-degree angle. So I'd have to go in the same order when I name the yellow one. 37, 53, 90, so that would have to be QHB. But this is not the only correct similarity statement that you could write. You could actually write any of these 6 options and they would all be correct because they all go in a corresponding order. Well, let's see if we can use the fact that these two triangles are similar to calculate their missing side lengths. For example, what if I wanted to know this side, the hypotenuse of this right triangle? Well, I do know the hypotenuse of the yellow triangle. And I know the lengths of both of the long legs of these triangles. So I could set up this proportion. 12 over 8, that's the long leg over the long leg, is equal to MR over 10. That's the hypotenuse over the hypotenuse. Then I can cross multiply and solve. So MR has to be 15 feet long. I could do something similar to find out the length of HB. HB is the length of the short leg, and I know the length of the short leg of the green triangle. So I can start out the same way of 12 over 8, that's long leg over long leg, and set it equal to short leg over short leg. Cross multiply and solve. Now you might be saying, well, wait a second, that's not how I wanted to solve. I don't want to use proportions. I want to use the Pythagorean theorem. And that would be equally as correct. You could say 9 squared plus 12 squared equals MR squared, and you would get the same answer of 15. Or you could say 8 squared plus HB squared equals 10 squared, and you would still get the same answer of 6. Both of those solving methods, using proportions and using the Pythagorean theorem, are equally correct for what we're doing today as well. Today we're going to be dealing with altitudes. An altitude of a triangle is a segment that connects a vertex of a triangle to the opposite side, so that the altitude and that third side are perpendicular to each other. For example, AD in the diagram we see here is an altitude of triangle ABC because it connects vertex A to side BC so that AD is perpendicular to BC. If we draw an altitude in a right triangle, we get some really special properties. If I draw an altitude, it creates a total of 3 triangles. We have the entire triangle that we started with, that's triangle number 1, and then I have 2 triangles on either side of the altitude. So that's a total of 3 triangles. And all 3 of those triangles are similar to each other. But you'll notice that they're all in a different orientation. Like this little triangle is sitting on its short leg and its long leg is straight up and down. But then the medium-sized triangle is sitting on its long leg and its short leg is up and down. And then the entire triangle is even different than that because its short and long legs are diagonal. So the first thing we're going to discuss before we go any further with talking about the similar triangles created by right triangles and altitudes is how to redraw a diagram so that all 3 triangles are in the same orientation and therefore easier to deal with. So what I want you to do is draw 3 triangles. The first one is just copy and paste of the original triangle, except you don't need to draw the altitude. So all I did is I drew this exact same triangle in the same orientation that I already had it, with the right angle in the top left-hand corner, and the short leg on the left, the long leg on top, and the hypotenuse going diagonally up and to the right. And I labeled it with its 3 vertices. Then I want you to draw this exact same triangle with the right angle in the top left-hand corner, short leg on the left, long leg on top, and hypotenuse going up and to the right. Draw that 2 more times. Make one a little bit smaller and one a whole lot smaller. These 3 triangles are in the same orientation because they all have their angles and their sides in the same places. They all have their right angle in the top left-hand corner. They all have the long leg on top. They all have the short leg on the left, and they all have a hypotenuse going up and to the right. So now we just need to figure out how to label the medium triangle and the little triangle. Let's start with the medium triangle. That's this triangle right here. The easiest thing to start out with for labeling is which angle is the right angle. For this medium-sized triangle, P is the right angle. So I'm going to label my right angle on this diagram with a P. Then I need to figure out which vertex is which. One vertex is the end of the short leg, and one vertex is the end of the long leg. So going from P along the short leg of this medium triangle, it leads to O. So going back to this diagram, going from P along the short leg, I end at O. Now let's do the long leg. From P along the long leg to the vertex on the other side leads to N. So from P along the long leg, I end at N. So let's do the same thing for our little triangle. Start by labeling your right angle. That's always easiest to start with. And this is my little triangle on this diagram. The right angle again is P. Then let's go from P along the short leg. That leads to M. And then P along the long leg leads to O. Now that I've redrawn the 3 triangles from this original diagram in the same orientation, it makes it much easier to write a similarity statement. For example, if I call the first triangle, the red triangle, MON, then I just follow that same pattern when I'm naming the other 2 triangles. So MON would be similar to OPN, would be similar to MPO. So the order of the letters in each of these triangles' names, I know have to go in the same order because of the way that I've drawn these diagrams to be in the same orientation. Now it's your turn. I want you to try to draw the 3 similar right triangles that you see in this diagram in the same orientation as the original diagram. Go ahead and pause the video and give it a try. Let's see how you did. The first triangle to draw is always the easiest because you just draw the exact same thing that you already had, but without the altitude. So I have triangle EGF. So now I'll draw 2 more of that exact same kind of triangle, just a little bit smaller and a little bit smaller still. Notice that all 3 of these triangles are in the same orientation. Their right angles are all pointing to the right. Their hypotenuses are all straight up and down on the left-hand side. And they all have the short leg on top and the long leg on the bottom right. So now let's label the medium triangle and the little triangle with their vertices. The medium triangle is this one right here. The right angle of that medium-sized triangle is called H. Then if I go from H along the short leg, it ends at point G. So if I do the same thing on my new diagram, go from H along the short leg, it ends at point G. Back to the original, if I go from H in the medium-sized triangle, along the long leg, it ends at F. So if I go on my new diagram from H along the long leg, it ends at F. And let's do the same thing for our little triangle. That's this little guy right here on top. Its right angle is called H, so I'll label this with H. And if I go from H along the short leg, it ends at E. So H along the short leg ends at E, and H along the long leg ends at G. Now that the 3 triangles are in the same orientation, it's easy to write a similarity statement. For example, if I call the first triangle EGF, then I would call the other triangles GHF and EHG because that would go in a corresponding order. Remember, this is not the only similarity statement that you could write. That's just the similarity statement that you would write if you chose to call the first triangle EGF. If you called it FEG, then you would be calling the other triangles FGH and GEH, for example. So there's a lot of potential correct answers here, but it's much easier to write this similarity statement if you've done this first step of drawing all of your triangles in the same orientation. Also, drawing all of these triangles in the same orientation makes the next steps way easier. The next steps is solving for each of the missing side lengths. Since the three triangles, which are created when you draw an altitude in a right triangle, are similar triangles, we can use proportions to solve for some of the missing side lengths. And since we're dealing with right triangles, we can also use the Pythagorean theorem to calculate side length as well. So let's try an example. Here we have a right triangle, triangle STU, and in this right triangle we have an altitude, altitude TV, and we need to solve for each of the missing side lengths. To get started, we're going to sketch each of the three similar triangles in this diagram in the same orientation. So the first thing I'm going to do is just copy and paste the original diagram, but without the altitude. So this is just triangle STU, and I labeled it with the lengths that I was told. I know that ST is 312, and I know that SU is 338. Now I'll draw two more triangles, one a little bit smaller and one a little bit smaller still, and label those diagrams based on what I see in the diagram. The medium triangle is this one right here. Its right angle is angle V, so I'll label this one's right angle with V as well. Then if I go along the short leg of the medium triangle, V ends at T for the short leg. And if I go along the long leg of the medium-sized right triangle, it ends at S. Additionally, there's one more thing that I can label. I know that ST is 312. We already had that labeled on this triangle, but ST also appears on the medium triangle. So I'll label 312 right here as well. Now let's label the baby triangle. That's this little triangle right here in the original diagram. Its right angle is called V. If I go from V along the short leg, it ends at U, and V along the long leg, that ends at T. Now, unfortunately, there's no extra sides here that I can label, so there's nothing else that I can put on my diagram. But I can write a similarity statement. If I call my first triangle triangle STU, I would have to call the other triangles SVT and TVU. So now let's use these diagrams to figure out the missing side lengths. The first length I'm asking for is TU. So first we have to find TU. I see one right here, and here's another one over here. It's really common to see a segment in more than one triangle. So for example, here's TU, but there's nothing else on this triangle, so I really can't use the little baby triangle to solve for TU because I don't know anything about it. But I also see TU on the big red triangle, and on this triangle I know two of the three sides. That means that I can use the Pythagorean theorem to figure out the missing side. TU is one of the legs, and so is 312. 338 is the length of the hypotenuse, because that's the side across from the right angle. So here we go. Leg squared plus leg squared equals hypotenuse squared. In other words, 312 squared plus TU squared equals 338 squared. Run those numbers through your calculator, and you get an answer of 130 meters. Now you might be thinking, oh my gosh, these numbers are so big. What are you doing to me, Mrs. Goforth? Well, there's a trade-off. Either I can make you problems that have really big numbers in their work, but pretty answers, no decimals. Or I can make you problems that have much smaller numbers, but really ugly answers. There's really no in-between with this kind of a problem, so sorry, but you do get really big numbers. That way you don't have to deal with ugly numbers for your answers. Alright, now let's solve for SV. You'll notice I updated my diagram. Both places that I see TU, I went ahead and labeled it with 130 meters. That's super important that you do that because you're probably going to need each of these answers in order to figure out other answers down the line. So let's see here. If I want to solve for SV, well, I actually only see SV in this place right here. That's one of the sides of this blue medium-sized triangle. But I only know one of the lengths in this triangle. So that means I can't use the Pythagorean theorem to figure this out. Instead, I'm going to have to set up a proportion. So looking at my other two triangles, which one do I have enough information on in order to set up a proportion? Well, that would obviously have to be the red one. So looking at the side lengths that I know and the side length that I'm looking for, what proportion can I create? Well, SV is the side that I'm looking for, and that corresponds to side ST on the big red triangle. So let's start there. I'm going to write 312 over SV. So that's the long leg of the big triangle over the long leg of the medium triangle. Now I need to set that equal to a ratio that is complete, that I know both the numerator and the denominator. Well, I only know one side length on the medium blue triangle, so I have to use the corresponding side length on the big red triangle. So I'm going to write 338 over 312. Then I'll cross multiply and solve, and I find out that SV must be 288 feet. All right, let's see what else we can do. So I labeled SV as being 288. We're getting closer and closer to having a complete diagram. Next up, we're going to solve for the length of VU. And I only see VU in one place again. It's right here. It's the short leg of the little triangle. And the little triangle, I only know one length. So I can't use the Pythagorean theorem here. I have to use a proportion. So I have to decide which of the other two triangles to relate to the little triangle to figure out the length of VU. In order to be able to solve for the length of VU, I need to pick a triangle that I know the length of its corresponding side. And I don't know the length of VT, that's the side that would correspond to VU, so I can't use the medium triangle. Instead, I'll use the big triangle because I know the length of TU, and that corresponds to the length of VU in the small triangle. All right, let's see what we can do. First, I'm going to write a ratio that's complete. For example, I know both the hypotenuse and the corresponding side that we're looking for in the little triangle, so I'm going to write 338 over 130. So that's the hypotenuse over the short leg in the big triangle. And I'll set that equal to the same ratio on the little triangle. So that's hypotenuse over short leg. So 130 over VU. Now you might be saying, well, hold on, I want to write my proportion in a different way. I want to write hypotenuse over hypotenuse equals short leg over short leg. Well, take a look. Wouldn't that actually be the exact same ratio? Proportions are kind of funny like that. As long as you're setting up your ratios in a corresponding way, you're going to get to the same answer no matter what. So I might write a different proportion than what you write, but as long as it's corresponding, you're fine. So let's cross multiply and solve, and I find out that VU must be 50 meters. There was actually an easier way to figure out the length of VU by going back to the original diagram. We didn't actually have to use a proportion at all. Since we had calculated in our previous step that the length of SV was 288, and we were given that the length of SU was 338, I can just use the segment addition postulate to figure out that VU is 50 meters that way. So on this kind of a problem, especially later in the problem when you've already done a bunch of solving, there's oftentimes going to be more than one correct way to arrive at an answer. Like our next one. If I want you to solve for the length of TV, there's actually a few different ways that you can do it. TV is right here on the little triangle, and it's also right here on the medium triangle. For both of these triangles, I know two of the three sides, so I could use the Pythagorean theorem to calculate the measurement. And it doesn't matter which set of measurements you use, you're going to get to the same answer no matter what. So let's say I wanted to use the medium triangle. Well, 288 is a leg, and TV, the missing side, is also a leg. 312 is the hypotenuse because it's across from the right angle. So the equation that I can write is that TV squared plus 288 squared equals 312 squared. And when I solve that out, I find out that TV equals 120 meters. And that's the basics of what you need to know about solving for missing segment lengths when you have an altitude drawn in a right triangle. In the next part of this lesson, we're going to explore how to use a geometric mean to help us solve for segment lengths as well.